All right, today we're going over circular permutations, which is really similar to regular permutations, but just a little bit different. So let's get into it. All right, so first, before we get into circular permutations, let's recall regular permutations. Okay, permutation, a regular permutation, it refers to the unique arrangement of a set of objects. Okay. All right, so let's say our set of objects were the three letters A, B, and C. Just as a quick example, these will be the 6 permutations that we can get as a result of having our set be equal to A, B, C. Notice that N is equal to 3 in this example, and K is equal to 3. By N, I mean N is the number of objects that we have to choose from, A, B, and C. And K is the number of objects that we must select. We must select all 3 objects, A, B, and C. But let's say we were only supposed to select, select 2 objects. Here, cross that out. Let's say we was only supposed to select 2 objects. Then, in that case, N will be equal to 3 because we still have A, B, and C in our set that we can choose from. But K will be equal to 2 because we're only, in each of these, notice that we're only selecting 2. And when N is equal to 3 and K is equal to 2, we still have a total of 6 different permutations as well. That's just how things just so happen to turn out. Well, no, not really. In general, P N K, P N N is equal to P N N minus 1. So here, let me start writing some stuff down. Better yet, this is what I'm saying. I'm gonna write down what I just said in a different color. I'm gonna write it down in yellow. In general, P N N is equal to P N N minus 1. Okay. All right. So I'm gonna move forward from here to the next page. Oh, whoops. Okay. So, just recalling the formula for permutations. PNK is equal to N factorial. PNK is equal to this stuff right here. Recalling where N is the total number of objects that we have to choose from. And K equals the number of objects that we must select. All right. So if I told you that we had the letters A, B, C, D, and E, that's 5 letters, but we only had to choose 3. We got to permute. We got to find every permutation of 3 of those letters. N would be equal to 5. K would be equal to 3. And that would be equal to, and the number of ways to permute that would be equal to, let's plug it into the formula. The number of ways to permute that would be equal to, I'll do it in a different color. The number of ways to permute 5 letters, when we must select 3 of those 5 letters, would be P, 5, 3, and P5, 3, and that is equal to 5 factorial over 5 minus 3 minus, that's a minus, look like a multiplication, minus 3 factorial, and that's equal to 5 times 4 times 3 when it's all said and done, which is equal to 60. I'll write it in that. Now I gotta erase some stuff. And 5 times 4 times 3 is equal to 60. All right, you get the picture. It's an ugly 6. It's kind of hard to write neat on this device. But all right. So moving forward, that was just a quick recall of regular permutations. I did that because we'll need those. They relate closely to circular permutations, as you may have imagined. Okay, so moving forward. Circular permutations. Now we actually talking about what we're here to talk about. All right, so circular permutations a circular permutation refers to the total number of arrangements on a circular structure. Okay. All right. So what does that mean? Let's look at an example. How many ways can you seat 3 people at a round table? How many different ways can you seat 3 people at a round table? A round table is a circular structure. Okay. All right. So let's go. Keep going. So right here, I got my different seats. Seat 1, seat 2, seat 3. And then I got A, B, and C. Those are my different people. Those are the letters that I'll be using to represent my people. So this is one arrangement right here. All right. This over here. All right. That's one arrangement. Now, over here, I'm about to do another arrangement. Over here, I'm about to do another arrangement. And let's see what I come up with. All right. So here on the left, I got one arrangement in which person A is in seat 1, person B is in seat 2, and person C is in seat 3. Whereas over here on the right, person C is in seat 1, person A is in seat 2, and person B is in seat 3. Now, if I were doing regular permutations, there is no doubt about it. These 2 permutations would be considered different permutations. But I'm not asking for a regular permutation. I'm asking for a circular permutations. And in circular permutations, this arrangement is considered the same arrangement. These 2 arrangements are considered the same arrangements. Okay, so even though A is in seat 1 over here on the left, and C is in seat 1 on the right, in the structure on the right, still, these are considered 2 different the same arrangement. Now, why is that? Why are they considered the same arrangement? Well, with circular permutations, what the uniqueness of a permutation is based on where the people are relative to the people that's around them, or not people, where the objects are relative to the objects around them. So in this certain scenario, we got objects A, B, and C. Now, if you look on the right, if you look over here on the here, let's focus on the left side first. If you look on the left, notice that A, if you go to the left of A, I know this is the right for us, but I'm taking it. I'm kind of considering from the perspective of a person that's actually sitting at a table. This will be the left of A. So if you go to the left of A, B is at A's left. And then if you go further, C is at B's left. And then C is at, I'm sorry, A is at C's left. And then it's the same here. So just a quick recap of what I just said. A is a person sitting down, and you look to A's left, and you have B. Over here, A is a person, and you look to A's left, and you have B. Okay? Over here again, B is a person, you look to B's left, and you have person C. Same over here. You look to B's left over here, you have person C. And then over here, if you look to C's left, you have A. And on the right, if you look to C's left, you have A. And that's why it's considered the same permutation. It's considered the same circular permutation. Now, it wouldn't be considered the same permutation if it was regular permutations, because they occupy different seats in these two arrangements. And the one on the left, A occupies seat 1, and the one on the right, C occupies seat 1. But it's a circular permutation. So we want to know how are they arranged relative to each other? How are the objects arranged relative to each other? And so let's figure out a way to count these. Well, first, before we get into the counting, let me see what else do I have next. All right. So, permutations and circular permutations. Okay. I want to compare the two real quick, just so that I can establish an algebraic relationship between the two, and then we can use that algebraic relationship to easily derive the formula for circular permutations. All right, so we got S1, S2, S3. Those are seats: seat 1, seat 2, and seat 3. Now, with regular permutations, these three permutations are all different. These are not considered the same. These are not considered the same permutation, as you know by now. But notice how. So look at the first one. This is the one we're focusing on right here. Okay. Notice how I got from here to here. How did I get from this permutation to this permutation? Okay. Notice all I did was shifted everything to the right. A was in position 1 up at the top, and now A is in position 2. B was in position 2, and now B is in position 3. And C was in position 3, and now C is in position 1. Since we ran out of room, you kind of got to wrap it around. But and then I just did that again to go from here to here. I just scooted everything to the right one time. These are all different permutations. But if we were looking at circular permutations, these wouldn't be considered different permutations. And I'll show you in a second, as soon as this finishes writing. These are all the same circular permutation. When we're considering circular permutations, these are all the same. Okay. Again, we're focusing on the right side, the circular permutation side. And why are they the same? Because if you look to the right of B in this top permutation, you have C. And if you look to the right of C, since we had to wrap around, the right of C would be right here. If you look to the right of C, you have A. And if you look to the right of A, you have B. Same thing in this one. If you look to the right of B, you have C. Same in this one. If you look to the right of B, you have C. If you look to the right of A, you have B. If you look to the right of A, you have B. If you look to the right of C, you have C. And if you look to the right of C here, you have C. Okay? So this is why they would be considered the same circular permutation. Well, I want to point something out in this video. Notice that going back to the permutation side, the regular permutation side, notice that one permutation, no, I'm sorry. Going back to the circular permutation side. Let's focus on this side right here. Notice that one circular permutation, because these three rows, this one, and this one, these are all one circular permutation. Notice that one circular permutation produced three regular permutations. Okay? One circular permutation produced three normal permutations. All right? Let's keep moving forward. Notice what is the importance of 3? What is the importance of 3? Let's see. I'll show you another example. Just so that maybe if you didn't catch on by now, let's find out what the significance of 3 is. But first, let me actually disclose to you the total number of ways there is to arrange, because I never answered the question yet. How many different ways are there to arrange 3 people at a round table? All right. Turns out there are just 2, and these are the 2 right here in front of you. These are the 2 ways to arrange circular permutations right here in front. These are the 2 ways to arrange 3 people at a round table right here in front of you. And why are these 2 different? Because if you look here in example 1 over here, if you look over here, focus your attention there. Notice that if you look to the left of B, if you look to the left of A and here, you have B. Over here, if you look to the left of A, you have C. If you look to the right of A, you have B. And over here, if you look to the right of A, you have C. Okay? So over here, B is on the left of A. Over here, B is on the right of A, making them two different arrangements. They are not the same circular permutation. 2 different circular arrangements. All right. And it turns out that that's the only 2 circular arrangements that you can, circular permutations that you can have when you only have 3 objects. In this case, the objects are A, B, and C, or people. I used A, B, and C to represent 3 people sitting at a table. But in general, anytime you only have 3 objects, and there's only 2 circular permutations. Okay, now let's try to derive a formula for circular permutation. I already gave you all of this. Turns out there's only 2 ways. And all right. What if there were 10 people? If there were 10 people at a table, how many different ways can we circularly permute 10 people? Now, you can see why we would want to come up with a formula, because you got to figure out all the different ways to permute 10 people so that they're not sitting in the same position that they were once sitting in when you once permuted them. And it's a headache. 10 people is a lot to be trying to do all that with. Even with 3, you may have had to think about it for a little while. And 3 turns out to be the smallest number there is. 3 turns out to have the smallest number of circular permutations. And even still with that one, you may have had to think about it a little bit. So 10, these numbers grow quick with permutations and combinations, period. So with 10, it'll become a headache. So naturally, we want to figure out, we want to find a formula. We want to derive a formula for circular permutations. And all right, next slide, I'll be showing you that formula. Or no, I won't be showing it to you. We'll be deriving it, which is even better. Oh, just a general rule of thumb on my channel. I never give formulas without deriving or proving the formulas. I always hated that as a student when a teacher will give me a formula without telling me where it came from. So I'll never be doing that. You'll always get a derivation of where the formulas came from. Now, and for future references, if you're only interested in the formula and you're only watching the video for the formula, that's cool too. But you'll always have to skip through and kind of find the point in the video where I actually give the formula, because I'm never gonna just open a video, tell you here's the formula, this is what it's used for, and this is how to use it. I'll always be deriving it, which is why my videos are always they'll always be long. Now recall A, B, C, D. We got A, B, C, D, D, A, B, C, C, D, A, B, and B, C, D, A. These are 4 letters. We got 4 letters. And let's say we had 5 letters to choose from. 5 letters to choose from. We had A, B, C, D, and E to choose from. And we got 4 slots to choose from. So in this case, N is equal to 5 and K is equal to 4. N is equal to 5. Here, I'll write that down. N equals 5. I can do better than that. N equals 5. K equals 4. Okay. Apparently I couldn't do better than that because that K is still pretty bogus. But the way that it's written, at least. All right, so N is equal to 5, K is equal to 4. These are all the same circular permutation. These are all the same circular permutation. Now, why is that? Again, let's look at every letter relative to the next one. If I start at A, I'm on this one right here. If I start at A, I move to the right, I end up at B. And then I move to the right, I end up at C. I move to the right, I end up at D. Now, I went in the order A, B, C, D. Let's try it. Let's see if we can do that again with this one. Oh, turns out we can. A, B, C, D. And again, A, B, C, D. And one last time. A, B, C, D. I want to point out this circular permutations are denoted as such. P circ and K. This circular permutation, P circ, this one circular permutation produce four normal permutations. Okay? So for every one, in this case, when K is equal to 4, for every one circular permutation, I get 4 regular permutations. Okay? All right. Now, again, I want to emphasize, notice that each circular permutation produces 4 regular permutations. Let's use that relationship between the two to derive the formula. Now, in this case, 4 was equal to the number of spaces that we had. So 4 was equal, K was equal to 4 in this case. But in general, K won't be equal to 4. K will be equal to K in general. We want to generalize our formulas. We don't want to make them in a specific case. Because what happens when K is not equal to 4 and it's not equal to 5? So, in general, here, let me go back to, I'll go back to the specific case first. In our specific case, the number of, now remember what I said. I said, each circular permutation produced 4 regular permutations. So for every one circular permutation you have 4 regular permutations. So naturally, the number of regular permutations, P and K, is equal to 4 times the number of circular permutations. And that makes sense because every single time we get every time we get a new circular permutation, it corresponds to 4 different regular permutations. So that makes sense that the number of regular permutations would be equal to 4 times the number of circular permutations. All right. Now let's go on to derive the formula. Whoops, gave it away too quick again. All right. So P circ is equal to, the number of regular permutations, P and K, is equal to the number of circular permutations, P circ and K, times the number of spaces that we have to select, K. That's in general. This is the general case, and which makes sense. If we had 5 spaces to choose from, then the number of circular permutations, each circular permutation would produce 5 unique regular permutations, and we can get all 5 of those unique regular permutations just by taking a single permutation. Let's say A, B, C, D, E was our regular permutation, and then we just shift everything over to the right by 1. And if the thing that's at the end, we just wrap it around. So E is at the end. I'm gonna shift everything over to the right by 1 and just wrap E around. A, B, C, D. And we could do that a total of 5 times. Notice that in this one, A is in position 1. In this one, A is in position 2. And then there's going to be another one where A is in position 3, and then 4, and then 5. And then if we do it one more time from there, we'll be getting back to our original permutation. So that was the case when K was equal to 5. But here, let me erase that. Okay. All right. So in general, the number of regular permutations, in general, the number of regular permutations is going to be equal to the number of circular permutations times K. All right. So how do we get, now we started this with the intention of finding out what P circ was. We are almost there. Can anybody guess what we do to get the formula for P circ? You guessed it. Oh, whoops. Let me go back. That's not all. Not just yet. That's what we do. All I did was divided K by both sides. Divided both sides by K. I'm sorry. I divided both sides by K and solved for P circ. And now we have P circ in a way that we can compute. We know the formula for P and K. We covered it earlier in the video. And we know what K is. Well, in the context of your situation, you will know what K is. And all you got to do is find the number of regular permutations and divide it by K. And that is all that I have. Hopefully this video was helpful to you. If you found the video helpful, feel free to hit that subscribe button. I will be making more and more videos. And if you need anything, put it in the comment box. I am taking recommendations. Right now, everything is pretty slow. So if you leave a comment and you know, for a request for a video, I'll be able to get it back to you within 24 hours. Have a good day. Good luck to you in all your mathematical endeavors, and see you next time.